A thermodynamic process is a passage of a thermodynamic system from an initial state to a final state. In equilibrium thermodynamics, the initial and final states are states of internal thermodynamic equilibrium, each respectively fully specified by a suitable set of thermodynamic state variables, that depend only on the current state of the system, not the path taken to reach that state. In general, in a thermodynamic process, the system passes through physical states which are not describable as thermodynamic states, because they are far from internal thermodynamic equilibrium. It is possible, however, that a process may take place slowly or smoothly enough to allow its description to be usefully approximated by a continuous path of thermodynamic states. Then it may be approximately described by a process function that does depend on the path. Overview. A thermodynamic process can be visualized by graphically plotting the changes to the system's state variables. In the example, 4 processes are shown. Each process has a well-defined start and end point in the pressure-volume state space. In this particular example, processes 1 and 3 are isothermal, whereas processes 2 and 4 are isochoric. The PV diagram is a particularly useful visualization of a process, because the area under the curve of a process is the amount of work done by the system during that process. Thus work is considered to be a process variable, as its exact value depends on the particular path taken between the start and end points of the process. Similarly, heat may be transferred during a process, and it too is a process variable. In contrast, pressure and volume are considered state variables because their values depend only on the position of the start and end points, not the particular path between them. Conjugate variable processes. It is often useful to group processes into pairs, in which each variable held constant is one member of a conjugate pair. Pressure, volume equals, the pressure-volume conjugate pair is concerned with the transfer of mechanical or dynamic energy as the result of work. An isobaric process occurs at constant pressure. An example would be to have a movable piston in a cylinder, so that the pressure inside the cylinder is always at atmospheric pressure, although it is isolated from the atmosphere. In other words, the system is dynamically connected, by a movable boundary, to a constant pressure reservoir. An isochoric process is one in which the volume is held constant, meaning that the work done by the system will be zero. It follows that, for the simple system of 2 dimensions, any heat energy transferred to the system externally will be absorbed as internal energy. An isochoric process is also known as an isometric process or an isovolumetric process. An example would be to place a closed tin can containing only air into a fire. To a first approximation, the can will not expand, and the only change will be that the gas gains internal energy, as evidenced by its increase in temperature and pressure. Mathematically, the system is dynamically insulated, by a rigid boundary, from the environment. Temperature, entropy equals, the temperature-entropy conjugate pair is concerned with the transfer of thermal energy as the result of heating. An isothermal process occurs at a constant temperature. An example would be to have a system immersed in a large constant temperature bath. Any work energy performed by the system will be lost to the bath, but its temperature will remain constant. In other words, the system is thermally connected, by a thermally conductive boundary to a constant temperature reservoir. An adiabatic process is a process in which there is no energy added or subtracted from the system by heating or cooling. For a reversible process, this is identical to an isentropic process. The system is thermally insulated from its environment and that its boundary is a thermal insulator. If a system has an entropy which has not yet reached its maximum equilibrium value, the entropy will increase even though the system is thermally insulated. Under certain conditions 2 states of a system may be considered adiabatically accessible. An isentropic process occurs at a constant entropy. For a reversible process this is identical to an adiabatic process. If a system has an entropy which has not yet reached its maximum equilibrium value, a process of cooling may be required to maintain that value of entropy. Chemical potential, particle number equals, the processes above have all implicitly assumed that the boundaries are also impermeable to particles. We may assume boundaries that are rigid, but are permeable to one or more types of particle. Similar considerations then hold for the chemical potentiale particle number conjugate pair, which is concerned with the transfer of energy via this transfer of particles. In a constant chemical potential process, the system is particle transfer connected, by a particle permeable boundary, to a constant micron reservoir. In a constant particle number process, there is no energy added or subtracted from the system by particle transfer. The system is particle transfer insulated from its environment by a boundary that is impermeable to particles, but permissive of transfers of energy as work or heat. These processes are the ones by which thermodynamic work and heat are defined, and for them, the system is said to be closed. Thermodynamic potentials. Any of the thermodynamic potentials may be held constant during a process. For example, an isenthalpic process introduces no change in enthalpy in the system. Polytropic processes. A polytropic process is a thermodynamic process that obeys the relation where P is the pressure, V is volume, N is any real number, and C is a constant. This equation can be used to accurately characterize processes of certain systems, notably the compression or expansion of a gas, but in some cases, liquids and solids. Main classes of process. According to Planck, one may think of three main classes of thermodynamic process: natural, fictively reversible, and impossible or unnatural. Natural process equals, only natural processes occur in nature. For thermodynamics, a natural process is a transfer between systems that increases the sum of their entropies, and is irreversible. Natural processes may occur spontaneously, or may be triggered in a metastable or unstable system, as for example in the condensation of a supersaturated vapor. Fictively reversible process equals, to describe the geometry of graphical surfaces that illustrate equilibrium relations between thermodynamic functions of state, one can fictively think of so-called reversible processes. They are convenient theoretical objects that trace paths across graphical surfaces. They are called processes, but do not describe natural processes, which are always irreversible. Because the points on the paths are points of thermodynamic equilibrium, it is customary to think of the processes described by the paths as fictively reversible. Unnatural process equals, unnatural processes are logically conceivable but do not occur in nature. They would decrease the sum of the entropies if they occurred. Quasistatic process equals. A quasistatic process is an idealized or fictive model of a thermodynamic process considered in theoretical studies. It does not occur in physical reality. It may be imagined as happening infinitely slowly so that the system passes through a continuum of states that are infinitesimally close to equilibrium. The fictive process can be regarded as reversible. See also, Kalina cycle, phase transition, heat, work. References. Further reading, Physics for Scientists and Engineers, with Modern Physics, P. A. Tipola, G. Mosca, Freeman, 2008, ISBN 0-7167-8964-7, Encyclopedia of Physics, R. G. Lerner, G. L. Trigg, VHC Publishers, 1991, ISBN 3-527-26954-1, ISBN 0-89573-752-3, McGraw-Hill Encyclopedia of Physics, C. B. Parker, 1994, ISBN 0-07-051400-3, Physics with Modern Applications, L. H. Greenberg, Holt Saunders International W. B. Saunders and Colorado, 1978, ISBN 0-7216-4247-0, Essential Principles of Physics, P. M. Whelan, M. J. Hodgson, 2nd edition, 1978, John Murray, ISBN 0-7195-3382-1, Thermodynamics, From Concepts to Applications, A. Shavit, C. Gutfinger, CRC Press, 2009, ISBN 9781420073683, Chemical Thermodynamics, D. J. G. Ives, University Chemistry, McDonald Technical and Scientific. 1971, ISBN 0-356-03736-3, Elements of Statistical Thermodynamics, L. K. Nash, Principles of Chemistry, Addison Wesley, 1974, ISBN 0-201-05229-6, Statistical Physics, F. Mandel, Manchester Physics, John Wiley & Sons, 2008, ISBN 9780471915331.